All right, guys, this is take 3, but you won't know that just because I told you. We are talking nuclear chemistry. This is our last unit of the year. I'm going to do 2 videos. This one we're going to talk about what nuclear chemistry is, and the other one's going to be half-lives and how to do half-life calculations. If you took earth science or remember anything from earth science, this is a bit of a review for this. But if you are going on to physics, you do some nuclear stuff. That's why it's kind of important. So that's why I want to make sure that we cover it. So this is going to be our last new unit of 2 videos, etc. And I'll give you a few, a simulation or 2 to play with, okay? All right, so we're going to start with nuclear chemistry. So far, everything that we've talked about in chem has been with the atom, but now we're going to dive into the atom, and we're going to talk about the nucleus of the atom, okay? So you know that in the nucleus of the atom, you have protons and you have neutrons. The electrons are on the outside, so we're generally going to ignore them. Isotopic notation is something that you should be sort of familiar with, but it's been a while. And so what that is there's your symbol, okay? Here's your mass number, and there's your atomic number, okay? So in nuclear chemistry, these are the same things, and we write things like this all the time. But we're going to write it like this. There's your atomic number. We're also going to call that the charge because that's your nuclear charge, right? This is the charge on your nucleus, so this is the charge of a carbon nucleus. So that bottom number is usually going to be the charge. Now your top number, oh, that's not what I wanted it to be. Okay, well, whatever. Sorry, guys, I'm learning. Okay, so this top number is your mass. Okay, and you can see a bunch of like important nuclear particles on table O. I know a bunch of you are like, I have no idea what my reference table is. That's fine, okay? But so nuclear chemistry, you're gonna see things instead of just like CO2, you're gonna see like nucleotides, like nuclei like this. And we're gonna talk about their charge, and we're gonna talk about their mass and how they change over the course of a nuclear reaction, all right? So let's move that. Here is an example of a nuclear reaction. Okay, so we're going to have nitrogen. Nope, let's do one that I actually sort of know. Let's do nitrogen again, misspell. Sorry, guys, losing it. Okay, carbon, 14. So what happens is this is an example of spontaneous decay. So this carbon-14, this is an isotope of carbon. It has a higher mass than standard carbon, okay? Standard carbon's carbon-12. If you looked at your periodic table, you see the average atomic mass is 12, okay? Yes, honey? All right, so that's regular non-scheduled break in programming was my daughter who needed help with something. So forgive me. Now you get 2 of me. Sorry, guys. So this is spontaneous decay. So what that means is that this carbon is heavier than a standard carbon, right? Most carbon has 6 protons and 6 neutrons, which gives it a mass number of 12. But this one has extra neutrons, which makes it less stable. So this is an unstable nucleus. And you know that because it's going to spontaneously decay. Now, carbon-14 decays via beta emission. And what that means is it spits out a beta particle, okay? So a beta particle is an electron. Now, think about that for a minute. This nucleus, which we just said has protons and neutrons, is spitting out an electron. Where did it come from? Well, that's where nuclear chem gets real weird, okay? So it's going to spit out an electron, and it's going to leave something else. So this is where we're going to change something from carbon to it's going to change to a different kind of nucleus. How do I know what's left over? Well, your top numbers have to be the same on both sides, and your bottom numbers have to be the same on both sides. And I'll show you what I mean by that. I'm going to do it in a different color so you can see. All right, so I have a total mass on the reactant side of 14. So I need a total mass on the product side of 14. Well, I know my electron has no mass, and I know that this thing has some sort of mass. Well, its mass has to be 14. 14 plus 0 equals 14. Beautiful. Now on the bottom, okay, I've got 6. My charge has to be conserved as well, right? So 6 equals, the arrow is always your equal sign, -1 plus, and then this unknown. I'm going to make that x. Now be careful here, okay? Add 1 to both sides. That becomes 7. Now how do I know what the symbol is? You're going to go to either table O or your periodic table. So if I'm going to my periodic table, I look up number 7 because this charge is what identifies the element. And I see that number 7 is nitrogen. And so that's what's left over. Now look at this. I'm taking a carbon nucleus and I'm turning it into a nitrogen nucleus. That's wild, but that's actually what happens in nuclear chemistry. Let's do one more example of that. All right, so we're going to do radium. If you've read Radium, girls, it's a good book. I think it's 88. Now here's radium, and this is also a spontaneous decay, and I'll show you what non-spontaneous decay looks like. But this is spontaneous decay. So there's radium, okay, and it's an unstable nucleus, and it's going to try to become more stable. How does it do that? How is it going to become more stable? It's going to spit something out of its nucleus. Its nucleus is going to spontaneously spit or emit something out, and it's going to make it become more stable. So radium spits out an alpha particle, which is a helium nucleus. So it's going to take 2 protons and 2 neutrons, and it's going to shoot it out, okay? And you're left with a helium nucleus. And then what is left? Let's do the same thing we did before, okay? I've got 226 equals 4 plus x. What's over here? Let's make that. That's going to be x, okay? So that makes it 222, right? 222 plus 4 equals 226. And then on the bottom, I've got 88 equals 2 plus x, and that's going to be 86. And then you would look up 86 on your periodic table and see that it's Rn, right on. All right? So that is how we do nuclear equations and how you kind of conserve the mass and the charge to figure out what you're left with. Now, a non-spontaneous reaction is called an artificial decay, and that's where nuclear fission and nuclear fusion come in. You may have heard of nuclear fission and nuclear fusion. Nuclear fission is division. It's like splitting a big, heavy uranium nucleus into smaller parts, and it's a big, crazy chain reaction. A fusion reaction is what happens in the sun and in stars, and it's where you take small nuclei and you fuse them together. So you take smaller ones and they fuse together to be larger ones. Fission is the one that happens in nuclear power plants. So if you've heard of nuclear energy, that comes from fission. That comes from some of the energy comes from mass. And if you've heard of that formula, that Einstein formula, E equals mc squared, you're actually converting a little bit of mass into energy. And so that's why nuclear power plants can give us so much energy. Here's an example of a fission reaction. So let's start with 238, 92 uranium. So we got a big nucleus of uranium. We're going to hit it with a neutron. So already you can see what's different, okay? What's different here is that I'm taking a uranium nucleus, which is unstable already, and I'm hitting it with a neutron as opposed to just letting it sit there and spontaneously decay. This one I'm like forcing it to decay. I'm going to use a neutron because it doesn't have any charge, so it can get close to that uranium nucleus. The problem in fusion is that we take things like hydrogen nuclei and helium nuclei and we try to fuse them together. This is also artificial, right? Because I'm hitting it with something as opposed to just letting it sit there. But this has a positive 1 charge and this has a positive 2 charge, and those things are not going to come together very easily. It takes crazy high pressure and crazy high temperature in order to do that. That's why it happens on the sun, but we can't do it yet on Earth, okay? So the uranium nuclei, let's go back up to fission. Let's say this is fission. And this is fusion. So the uranium nuclei gets hit with a neutron, and it breaks apart into 2 smaller nuclei. Now, I don't remember these numbers, so I'm going to do the best I can. It depends. I think krypton and barium are 2 common ones, and then you get 3 neutrons out of it, okay? The total here plus here plus here is going to equal here, just like we did above, okay? But what's different here is now I've got 3 neutrons, okay? So let's think about it. I've got 1 neutron. That 1 neutron produces 3. Each neutron, my daughter is crying again. Hold on, Riley. Produces 3 more. And you can see this chain reaction getting crazy out of control because you're releasing a ton of energy. These are super exothermic. Nuclear stuff is really important and it's really beneficial. We use it for a lot of things, okay? So we use nuclear tracers to trace chemical reactions, and we use radioactive iodine to treat thyroid disorders, and we use radioactive cobalt to do radiation in cancer treatments. We use radioactivity, we radiate our food to kill organisms, and there's a lot of benefits to this kind of radioactive stuff. Now, if you're Will, you know a lot about this because you have watched Chernobyl a million times and asked me if we could watch Chernobyl a million times. Well, if you want to, please go watch Chernobyl. I'm kidding. I've never seen it. I can't say that that's a good thing to watch, but there are definite risks when it comes to nuclear chemistry as well. Half-lives, nuclear waste that doesn't decay quickly, etc. But that's a little bit of an intro to it, and then we're going to talk about half-life in another video. Awesome. Thanks. Bye, guys.